Okay, let's flip the scale inhibitors. Okay, so how do we stop scale formation? Basically what we do is we actually, the scientists were pretty good, the chemists were pretty good. They actually invented what they call organic phosphonates. And basically when calcium carbonate forms, it forms in a crystal, okay? And that crystal actually compacts. You know, one on top of the other, forms nice layers, and you get a nice layer of scale formation. It's all usually pretty even. So it forms a nice compact, and they fit in nice little segments, and that's how you grow scale formation. What the phosphonates do is they actually modify that scale. So as calcium and carbonate come together, the phosphonates get their finger in there, okay, basically, and they modify that crystal. So now it's not an organized crystal anymore. So it's trying to find a slot for itself. Can't find a slot. Can't find a slot. Eventually gets purged out of the blowdown. So it's basically a crystal modifier is what we do. And if you want to look at it from an electron microscope standpoint, you can see the crystals kind of up in this area here where they're nice cubic in some shapes. There's ones that are starting to form on top of each other. And then of course when you modify them with the phosphonates, you can see how they're all distorted and everything else. So they really can't form a deposit. They basically run around the system and eventually either settle out somewhere or go through the blowdown. Scale inhibitors for choice in Seattle. Okay, let's figure out what you should be using. There's a couple different scale inhibitors used around the country. There's basically only two choices that are technically sound for the Seattle water. If you're going to push your high cycles, which are 15 cycles of concentration, I recommend the use of PBTC phosphonate. Okay, basically this is a phosphonate designed to handle high scaling water because we're actually making scale. We're actually driving the water to a scale forming state. And so we certainly want to make sure we don't scale the system. So a PBTC phosphonate blend, most water treatment companies have a polymer they use for suspended solids, and azole. Azole is your copper corrosion inhibitor, and we'll talk about that. If you find that you need additional corrosion protection, if you choose not to run 15 cycles, even at 15 cycles you still see some corrosion you don't like, the other program is what they call HEDP phosphonate plus zinc, and then polymer and azole. Now some municipalities restrict zinc, so you need to be aware of that in case that's a problem up here. But basically the zinc is a cathodic inhibitor. It basically forms a cathodic barrier on the steel surface to help protect corrosion. HEDP has the advantage that it kind of breaks down over time, so it breaks down to orthophosphate. So you have some orthophosphate in the system over time. That also is a form of corrosion inhibitor. So I don't think you'll have corrosion problems if you run 15 cycles. My recommendation would be the PBTC, polymer and azole, but if you do need help, certainly there's two programs. If you're running any other type of chemical programs outside of that, you're probably not where you should be on that. Most water treatment companies have these two programs, and these are two programs of choice, so you're probably already there. Both of these products come in a one drum formulation. Okay, so you're basically buying one drum. They have the formulation on there, so it's very easy to apply with a small chemical pump and based on the controller. Okay, corrosion control. We don't really do a whole lot when we have scale forming water. If you look at water, it either wants to be corrosive, it wants to take minerals to satisfy itself to be stable. There is a point where it's actually stable. These are where the nuclear power plants run. People that run water out of Great Lakes and run into nuclear power plants for condensers, they can't discharge that water back to the Great Lakes with chemicals. They can't discharge it to the groundwater. So what they do is they actually adjust the water quality so it's very non-corrosive, non-scaling. It's right at that middle point. Now that's difficult to do, but they have the time and the resources to do that. Or you make the water scale forming. So in other words, the water has got so many minerals in it that it wants to give it back to you, okay, at scale. So we can do whatever we want. If we want to make the water corrosive, we can just feed acid and bring the pH down. And that used to be the program of choice back in the early 80s, if you remember chromates. Very inexpensive program. We had pH to bring the water to a corrosive state. We fed chromate for corrosion control. Well, chromates were outlawed in 1987 as a suspected carcinogen. So now what we're doing is we're driving the water up to a scale forming state, so it's not corrosive anymore, and we're feeding a scale inhibitor. So most of the corrosion control is done by cycling the water up. One of the things that you want to do to make sure that things are going well is put in a corrosion coupon rack. And these are basically racks where we have small pieces of metal strips, and they're pre-weighed to the 4th decimal point, so there's a known surface area, a known weight, and we actually put them inside the corrosion coupon racks, and we actually simulate a 3 to 5 feet per second flow, which is what you're seeing through the system normally. And we set that through a water meter where we controls at 5 gallons per minute. So normally a 5 gallon per minute rack, 1-inch rack, will simulate 3 to 5 feet per second. And the goal is you pull those coupons out about every 90 days, okay, and you have them cleaned and reweighed, and that tells you your mills per year thickness. So it gives you about 4 or 5 indications per year before you open up that chiller, so you're not surprised at what you see. And normally what we want, again, mild steel should be less than 1 mil per year, copper less than 0.1, galvanized, if you have a galvanized tower, you should have less than 1 mil per year on the galvanized too. If you're exceeding those limits, that just gives you an opportunity to make adjustments to the program and find out why before you get the magical surprise when you open up the chiller. One of the corrosion inhibitors copper corrosion inhibitors is azole. Okay, this is basically a film former on there. For all your chemistry guys, I gave you the 2 molecular chemical formulations right there. Basically, there's 2 types. There's tolutriazole and benzotriazole. Basically, this is added in the chemical and actually puts a coating, a molecular level coating on the copper surfaces and acts as a barrier. So really the corrosive water really doesn't come in contact with the pipe surface itself. And we normally want to carry about 1 to 2 parts per million of azole in the system on that. So I know that when you get all your service reports from your water treatment suppliers, I'm sure there's going to be a nice little quadrant that says azole, you know, and they're going to have a nice little number right there, and it's going to be in range. If they don't have it there, you should make sure that they do have it there, because that is your only source of copper corrosion control. Okay, and the last quadrant we talked about is fouling. Okay, and basically, like I said earlier, if you stand next to a cooling tower, your cooling tower acts as a big air washer. Okay, so if you're next to a road or next to a construction site or next to a high dust area like in Phoenix or Vegas, there's a lot of suspended solids that comes into the cooling tower because it actually cleans the air. That's one of the advantages of it. Unfortunately, the dirt particles go through your system, so it has a chance to be captured on the pipe surface or the heat exchangers, and it also settles in your tower basin. Okay, what we want to do is we want to make sure that we remove or reduce the amount of loading of particulate matter, because it's also a transport mechanism for biological activity. It's like they hitchhike, grab a ride on it, and they go around the system until they want to settle out somewhere. And of course, you can see the cooling tower base and all the mud and debris and everything else that accumulates in the cooling towers. So in order to remove suspended solids, you have a couple options. One, you can do more blowdown, which is against the thought process of trying to conserve water. You can do more tower cleanings, which is certainly recommended by OSHA, or you can look at filtration. I'm not going to talk a whole lot about filtration because there's a segment coming up on that, but one of the things that you need to look at before you put filtration on there is determine what filtration unit you want to put on there, okay? And there's a couple different filter units that you have a choice of. And this is kind of an industry problem right now because a lot of people are putting on filters that are the wrong filters for the cooling towers. Okay, one of the things that you want to do is you want to do what we call a particle size distribution. We have the ability to take a water sample, even as clean as it might be, and run it through a counter, a particle counter. Okay, it will actually tell you how many particles you've got in the different micron size capacities. And these are micron is basically the thickness of the particle. It's the width of the particle. So here you have 0.5 to 1 microns, which is 1/1000th of an inch, okay, all the way up to 100 micron. Trivia question. Assuming you have 20/20 vision, do you know what micron size you can see? Anybody going to take a guess? 0? I'm assuming 20/20 vision, sir. Anybody want to take a guess? 5 to 10? Anybody else? 20? Anybody higher? 50? Getting closer? Yeah. Actually, it's 40 microns. A normal 20/20 vision can see a 40 micron particle or above. Me, it's about 100 micron. You know, I just can't see up close anymore. So you can see that 40 micron, 50 microns is really when you start seeing a particle, okay? So if you have things like dirt and debris, bugs, leaves, those obviously are much larger micron size. You can see all that. But look where all the particles are at in this cooling tower. In the cooling tower here, you have 306,000 particles per milliliter of water. in the 0.5 to 1 micron range. At 40 micron, you've got about 90 or less up there. Okay? Filters are rated in micron size. So if you had a 40 micron filter, what do you think your chances are of being an effective filter for this tower? Not very good. Okay. So you're going to make sure you do a particle size distribution. Most of the most prominent one is the sand filter units. Okay? And you'll hear more about that a little bit later. The other thing that we have, and probably the best thing that has occurred in the water treatment field in the past 4 or 5 years, is the feed automation. The controllers have really taken a quantum leap in the ability of controlling the chemistry. These meters right now, whether it's a Webmaster, Advantage, or Tracer, or whatever the models you have, now have the ability to do things like conductivity, to blow down, ORP, which is your biocide feed. Some are trace, where they can actually measure the chemical levels themselves and bring it back into the controller. They have flow switches to let you know if the system's on or off. They can actually have feed verification on the pumps. Does liquid actually go through the tubing? You know, the controller says, turn on my pump, but how do you know there's chemical going through there? They can actually feed and verify that the water is going through there, or the chemicals are going through there, and everything can be web-based. So you can almost be now at a computer and see your entire water treatment program in there. And that's important because as you push the cycles and as you push the chemistry, you need to make sure you have good automation. So I would encourage each of you to look in that, and also it can take water meter signals and actually calculate how much water you use per day and everything else. And that would be different from the program that they're talking about earlier. But I would encourage you to look at some of the controllers. They're very good, they're very effective, and they're fairly accurate. Just to give you an example, back in the 80s, we did a lot of manual control. Obviously, you would not think the control was very good. Then we started feeding by bleed. So in other words, as the bleed solenoid valve opened up, we'd feed chemical with a thought process. As you bleed, you lose chemical, so you want to replenish it at the same time. Better control. And then you start feeding it based on water meter or inhibitor trace. We can lock it in pretty close. So the technology is fairly good on those controllers, and you should look at some of that. Pricing is coming down on that automation, so it'd be worth looking into. Okay, so what's the problem that we see out there with water treatment? Well, back in July, from January to July, we tested 1,188 cooling towers, okay, in our labs. 50% didn't have enough phosphonate for scale control. 30% didn't have enough azole. 18% had excess bacteria counts. 90% of the chilled water loops did not have the right chemistry. That's not good. The technology is here. The automation is wow. Then why are we not implementing this program very well? So I guess my question to you is work with your water treatment suppliers. Challenge them. Challenge them on that. Adjust the blow down and run your 15 cycles. That should be your homework assignment for tonight or tomorrow. If your water treatment supplier says they can't do that, then change suppliers, basically. Okay? Is there an alternate water source available at your facility that you can use? And rethink about that. You can have that analyzed and see if it's worth bringing it back to the cooling tower if our return on investment is there. Next question is, how's your biocide program? Okay, that's the 90% rule theory. And then certainly reevaluate your water treatment automation program. And I think you guys can amplify your water treatment program, push those cycles the way you should be, get that water conservation, and get some great results. So that's it for me. Any questions?